All right. So today we want to revisit the homework problem I assigned last time, and also I give you this some kind of hint, right? So I'm going to talk about this. So the homework number 2 is pretty simple. It's about the ask. Suppose you have a set S and you have an upper bound. It turns out that this upper bound belongs to S, and you want to show that this upper bound is actually the least upper bound, the supremum. And last time we give this hint, I believe all of you may have already solved this problem. But here I just want to demonstrate the writing of this proof. Okay, there are a couple ways to write this. They all can use different way to express the key proof. Now here, one way to do this is the following. Okay, so you think about the problems. So there is a upper bound, right? They talk about upper bound. So let's say that this upper bound is U, denoted by U. This is the upper bound of S. And by the assumption, we're talking about upper bound belongs to S. So let's assume that U is belong to S. Okay, so what we want to prove is that this is a supremum. This means that we want to show that U is the least upper bound. Now, in order to show U is the least upper bound, you're trying to show that U is less or equal than any other upper bound. Okay, so let's say that V is another upper bound, it's an arbitrary upper bound, okay? Now, by saying that V is a arbitrary upper bound, is an upper bound, what does it mean is that S will less or equal than V for any S in S, okay? So that's a definition for V to be upper bound. Now, by the assumption, we know that the U is already in S. So obviously U will be less or equal than V. So from here, you can conclude that the U is actually less or equal than any other upper bound. Therefore, U is the least upper bound. So this is a simple way to write this proof. Okay. There you can argue for another reason in another way. You can, if you have a different way, that's fine. Okay. All right. So this is the number 2. The number 3 is that let's say you have an S, and then you have an S naught is a non-empty subset, and you want to show that these infimum and supremum will satisfy this relationship. And last time I demonstrated one side of the proof already. Okay, so here I just so this one I think there's no problem for you to write the proof. I just want to indicate the paragraph, how to arrange this paragraph. Okay, so you trying to show the left inequalities. Okay, left side, the first inequality. Okay, so this is done last time already. So I just copied on the last argument. So you know that. Okay, so this is the first paragraph and showing the first inequality sign. And then you go to the next steps, the middle inequality. And I mentioned last time that the middle inequality is obvious. So you can say that by the definition of infimum or supremum, so this middle inequality is obvious. You don't have to do any proof. And for the third inequality, you need to include another proof, which is parallel to the first paragraph. Okay, so this is the arrangement of this writing. Okay, so maybe this is helpful to you when you begin to write this proof. Okay, so this is the homework number 2, number 3. And then I will also talk about the Archimedean theorem. Okay, we proved this last time, right? Okay, so now you understand this proof, but I want to indicate that in this proof there is a key argument. The key argument is the following here. The key argument is that once you get the least upper bound, you're trying to reduce it by U minus 1. You say that, of course, U minus 1 is no longer an upper bound. So therefore, then you can use 0, 1.5, or just using the definition of upper bound to show that, to conclude that there exists M okay, there exists elements such that u minus 1 is less than m. Okay, this is just because u minus 1 is no longer upper bound. Now, because of this, then you move the minus 1 to the other side, you get u less than n plus 1. So this will give you a contradiction because n plus 1 will still be in n is an integer. How come this integer is greater than its upper bound? That's impossible. So this contradiction shows that the actually the theorem is true. So the key step here is once you have the least upper bound, you reduce it to a lower number. So you have to have u minus 1. Now you can reduce it to u minus 2 or u minus any integer. Then same argument works. But because eventually you will get u less than m plus integer. M itself is integer, then the other one is also integer, then the sum is also integer to conclude the contradiction, right? Now, I want you to think about this argument, okay? Apply this to a different situations. For instance, you can think about the following. And we want to prove a different theorem, okay? So we want to show that for every x, okay, there's always has a rational number, Rx. Now, previously, we were talking about integers. Now, this time we talk about rational number, okay? This rational number is denoted by Rx, meaning that the Rx is related to x, such that x is less than Rx. So these are brand new problems. And you just replace the integer by rational numbers, okay? But you can see that the same argument works. Exactly the same argument works, okay? So let's go through it. Okay, we're still using the method of contradiction. Now suppose you're given x, there's no such Rx, then this means that any rational number will be less than x, right? Less or equal to x. So this means that x will be an upper bound or q. Now q stands for set of rational number. And then you argue with the same argument. So by the supremum properties, so there must exist, okay, least upper bound u for this q. So this means that R will be less or equal than U for any R in Q. Okay, so you reach the same kind of conclusion here, just like in the whole number case. Now, then you argue the same way. So suppose U minus 1 is not a upper bound. Now since U minus 1 is not upper bound, so this means that there is a rational number, okay? It's greater than U minus 1. And then you do the same thing. You move the 1 to the right side. You're getting u is less than r plus 1. And this will give you a contradiction because on the left side, u is the upper bound of q. So you're supposed to control all the rational number. But on the right side, you have r plus 1 is a rational number. So that specific rational number controlling u, that's impossible. So therefore, this means that u is no longer upper bound. This is a contradiction. Now, so we see that the same argument works in this case, right? But I'm trying to point out here is the you know the key step is to replace u by u minus 1, right? Now this one, instead of reduce it to u minus 1, you can reduce it to u minus r naught. U minus r naught. Here r naught is a positive rational number. You don't have to use integer. Integer is a rational number. Actually, you can reduce it to u minus r naught, okay? Why? Because if you do that, you still will get a contradiction because then you will see that in the final step, you will have u less than r plus r naught. Now, r is a rational number. R naught is a rational number. So therefore, the sum is a rational number. Then you still get you the contradiction. Okay. So you can see that in the proof, you can see in the same argument works, and for this detail, okay, the reduce u to u minus 1, this detail, and can be, instead of reduced by 1, you can reduce by or not, a rational. Okay. So this is a variation of the previous theorem. And you can continue to make a different problem instead of like, suppose you're thinking about the, suppose you're thinking about an irrational number this time. Okay, so you replace the r q by r minus q. So this means r minus q is the set of irrational numbers. So for any x given x, and there must be an irrational number ix controlling x. You can see the same argument works. The same thing works. Okay. Now initially you set you're starting from u here. You reduce it to u minus 1. Eventually you have u less than I plus 1. You still get into the contradiction because I is irrational. Then I plus 1 will still be irrational. Okay? So this means that u is not an upper bound for the irrational number. You still get a contradiction. But the reason I'm showing this proof is because that I want you to think about this case. Now, again, if you replace the u minus 1 by u minus r naught, r is a rational number, then it still works. Why? Because eventually you will get u less than I plus r naught. Now this time I is irrational, and I is irrational, r naught is rational. So you know that irrational plus rational is still be irrational. Okay, so this indicates that this I plus r naught controlling this upper bound, that will give you a contradiction. But later I'm going to show you that why. In another situation, we can indicate, have a proof about why the irrational plus rational is always irrational. Okay, now, so here I want to point out that here you're still using reduce it to u minus r naught, which r naught is rational, even though you're working with irrational. But however, you cannot reduce it to u minus I naught. Okay, here I naught is irrational. You can't do this. The reason is because that if you replace u minus 1 by u minus I naught, then you will get eventually u less than I plus I naught. Now, in this case, you can see both I and I naught are irrational number. And we know that if you have two irrational numbers, the sum may not be irrational, maybe irrational, or maybe integer. So that's why in this argument for the irrational number, you cannot replace it by I naught, by irrational. Okay, so this is some kind of extended discussion of the proof for this Archimedean theorem. Okay. All right, so this is a kind of review for the previous lecture. And do you have any questions? Okay, if no questions, then we'll begin to think about the existence of square root. Actually, last time we have already started the proof, right? So again, I'll repeat a few of the procedures, okay? Then we'll get to the new part, okay? So prove the existence of square root 2, meaning that you're trying to show the existence of x, okay? A positive number x, such that x squared equals 2, okay? So this is our goal. Now, in order to reach this goal, we use a very special argument. So we're trying to define a set, it's called S. S equal to all the real numbers such that x squared less or equal than 2. Now, the reason we look at this set is because that if you're just asking for the solution for x squared equal 2, then you don't know where the solution exists, right? But by replacing equal sign with the less or equal than inequality sign, then you can see this S is not going to be empty. This S carries many, many numbers, okay? For instance, 0 is inside this S because 0 squared is less or equal than 2. 1 is inside because 1 squared is less or equal to 2. There's a many, many number inside. Okay, then we can work on this set. Now, the first step to working on this set is to show that this set is bounded above. Now, how do you see this is bounded above? Okay, you think about it this way. Now, suppose you have x in S. So this means that x squared by definition, x squared is less or equal than 2. But 2 is less than 4. Okay, I'm trying to replace 2 by a bigger number, so therefore I can take a square root on both sides. And then you get a new control. So thinking about x squared less than 4, and then you take a square root on both sides, then you'll get x is less than 2. So what this means is that we have a set S, and then 2 turns out to be an upper bound of S. So you can conclude that this S is bounded above. Now, once it is bounded above, then we know that by the supremum properties, S must contains the least upper bound, okay? So let's say that this least upper bound always exists. So we call this least upper bound by S. So S is the crucial number we're going to look at. So by the supremum property, we know the existence of this S. And now we're trying to show that this S is just the solution for x squared equal to 2. Okay, so in the rest of the proof, we're trying to show that x squared equal to 2. And once you can do this, then we just got a solution. So we finish the proof, right? Okay, so now come to the problem. How do you prove that x squared equal to 2? And again, we use a very special way. Okay, we're trying to show that s squared is greater or equal than 2, and at the same time, s squared is less or equal than 2. Okay, if you can establish both inequality, so in order for both inequality to be hold, then s squared has to be exactly equal to 2. Okay. Okay, so for instance, suppose you want to show s squared greater or equal than 2, and then we're trying to argue this by contradiction, okay? So apply the contradiction method on this part of the proof. So by using contradiction method, meaning that s squared, assuming we begin to suppose s squared less than 2, and trying to get a contradiction with it. That's argument for s squared in order to show that x squared greater or equal than 2. And we're trying to use a similar argument to prove the other side, s squared is less or equal than 2. So let's look at this first. Now, for a lot of time, when you begin trying to sketch a proof, especially in the mathematical analysis area, if you want to sketch a proof, sometimes you need to prepare a scratch paper and do some analysis. So let's say that I have a scratch paper here, and I'm trying to do some analysis. Okay, then I can write down the detail. Okay. Okay, on this scratch paper, I draw a line. And showing that there's the point 2 and the square, s squared. So s squared is less than 2, okay? So this means that between s squared and 2, there is a gap in between, right? So the key argument is that we're looking for a small number, 1 over n. So if suppose n is integer large enough, so 1 over n can be made any smaller than any number, right? So when we're thinking about that, since s squared is less than 2, so I can choose a small number, 1 over n, add it to the s, then the square of new number is still less than 2. The reason you can do that, of course, at this stage is not obvious, but by the common sense, you can see that this n always exists because we have a gap here. So in the first step, we are trying to find out how large the n should be in order to make this happen. Okay. In other words, we want to try to solve inequality. Okay. We want to find n. Okay. Find a restriction on n so that the s plus 1 over n squared is exactly less than 2. Okay, now how do you solve this inequality? I make expansion, s plus 1 over n, the expansion, the square. So the expansion will equal to s squared plus 2s divided by n plus 1 over n squared. Now, if you just solve this inequality, saying that this return is less than 2, trying to solve this inequality to solve n, then it's not easy because this on the left side, I mean the two terms before this inequality, okay, the two terms before this inequality actually involve what? Oh, there's a question. Why use 1 over n instead of n to describe the space between? Because n is considered as integer. N is a large integer community, right? Okay, so 1 over n is a small number. Okay, because the gap is small, so that's why you're looking for some small number added to s, so that the square of this still inside the gap. If you just replace, for instance, s plus n, then s plus n will never, the square of this will never be less than 2, because the difference is 1, at least 1. But 1 over n, the difference maybe like a hundreds, okay, 1,000, something like this. So it can be small. It's possible. Okay, so here we come down to trying to solve the inequality. So the s squared plus 2s over n plus 1 over n squared is less than 2. As I can say that it's difficult because it's involved the n squared. This means that we're dealing with a quadratic inequality. It's difficult. So what we're trying to do is we're trying to simplify this first. But really, we don't want to solve the whole inequality like this. We only need to, you can replace 1 over n squared excuse me, by 1 over n. I can remove the square. Because if you remove the square, then 1 over n getting bigger. So the sum s squared plus 2s divided by n plus 1 over n squared. So this sum of these three terms will less than that term. The s squared plus 2s over n plus 1 over n will be less than that. Okay, instead of to solve the full inequality, now you just solve this new inequality. Once n satisfies this new inequality, will automatically satisfy the previous inequality, right? So there's no problem. And the good thing is that you can see there's no n squared, so that's 4. This inequality is a linear inequality, so it's easy to solve. So you can combine, now to solve this inequality, you can just combine 2s divided by n plus 1 over n together. Okay, and then you combine s squared minus 2 together. So put everything in the right format, so you will get the solution of this inequality is 1 over n is less than 2 minus s squared over 2s plus 1. So this means that, you see, s squared is given, is a fixed number. 2 minus s squared is the gap, right? The measure of this gap. It's a fixed number. Divided by 2s plus 1 is another number. So on the right side is a fixed number. So this inequality tells us that as long as 1 over n is less than this fixed number, then the s plus 1 over n squared will be in the gap. Okay, so this is our purpose of solving this inequality. Now, why is such a 1 over n exists? This is guaranteed by the corollary 1.8b. Okay, so this is guaranteed, always guaranteed. So this means, so at this stage you can see that I can always find 1 over n, so that this new number, the square of this new number is in the gap. So now I can continue, okay, continue the proof. So first, in the proof, in the next sentences, I want to claim that there is an n, okay, so that 1 over n is less than this. Okay, because this is you can cite this. This is based on the corollary 1.8b. Okay, there's always such n, right? Okay, so based on 1.8, so such a 1 over n, so this inequality is always satisfied. Okay, for such a 1 over n. Now then you are going backwards. Okay, going backwards. So this inequality meaning that this will imply that s squared plus 2s n plus 1 over n is less than 2. I mean, that's just a manipulation of the previous inequality. You get this one because based on our computation on the scratch paper, okay? And then this will imply that the s plus 1 over n squared will be less than 2 because s plus 1 over n squared, the expansion equals to the sum of these three terms with the n squared, right? But know that the 1 over n squared is less than 1 over n. So therefore, you can see the s plus 1 over n squared is less than 2. Okay. Okay, so we spend a lot of time working on the existence of such 1 over n so that s plus 1 over n squared is in the gap. It's less than 2. Now, what for? Why this is useful in the proof? Because these things will tell us, will actually give us a contradiction. I mean, as long as s is the least upper bound, okay? The least upper bound of this s. And then it is impossible for you to have such things like s plus 1 over n squared is less than 2. You cannot get this. Why? So if you have s plus 1 over n squared is less than 2, so this means that the s plus 1 over n is inside the s. That follows from the definition of s, okay, the set s. Because any number in this set of s, the square of this number is less than 2, right? Less or equal than 2. Now I got 1 over s plus 1 over n squared is less than 2, so this indicates that the s plus 1 over n is belongs to s. Any questions? Now, pretty soon we are going to see the contradiction. But immediately you can see that this contradict to the fact that s is the upper bound. Now here we know that s is the least upper bound, but here least upper bound is upper bound, right? So this already contradicts to this fact. Why? Now you think about it. S is upper bound of s. How come there is another number s is greater than s? Because s plus 1 over n is greater than s, right? How can such a number exist in s? So that's why you get a contradiction. So this contradiction basically shows that the s squared less than 2 is not possible. In other words, this means that s squared is greater than or equal than 2. So that's the proof part 1. Any questions? So, so the proof is, I mean, the writing is not long, it's like this, but here, and the idea of proof, this argument needs to be reviewed after the lecture, okay? And you're trying to understand all the steps here. Okay, so now let's go to step 2. Step 2 is s squared is less or equal than 2. And again, we'll choose to prove it using the contradiction method. So using contradiction method, meaning that we're going to prove that s squared is greater than 2. Okay, so we're in the opposite situation. Previously, it's s squared less than 2. Now it's s squared greater than 2. But then you can compare, again, the s squared and the 2. You can still see that there's a gap. But only this time, the gap is on the right side of 2 instead of left side of 2. So again, we're trying to do something in the scratch paper. So you can see now is the situation. So s squared now on the right side. Okay, so there's creating a gap on the right side. Now we're trying to use the same idea, trying to get a contradiction, right? So I'm going to thinking about this gap. Okay, so this time, now previously I increased the s a little bit, right? Increase s a little bit, so that the number is still in the gap. Now this time, since s squared is on the right side, it's greater than 2. So I have to decrease s a little bit. Okay, decrease s a little bit. And also I'll make sure that this decreased number, the square of the decreased number, still in this gap. So what does it mean is, now this time choose 1 over n, subtract from s. Okay, so it's getting smaller number. The square of the smaller number is still greater than 2. Now this is the key step. So first, as we did before, we had to work out this n, okay, to see why such n exists. Now once you get this inequality, then you can from there trying to derive a contradiction. Okay. Okay, so this means that we want to solve this inequality, right? Make expansion. S minus 1 over n squared. So this have 3 terms there, right? Now this time the inequality is on the right side, s squared minus 2s divided by n plus 1 over n squared. So the sum of these 3 terms should greater than 2. Should greater than 2, okay? And again, you cannot solve this inequality directly because you have n squared involved, and then this inequality will become complicated. It's like a quadratic inequality. Okay, you're trying to simplify it. Now remember that this time the situation is opposite, okay? You see, the inequality is greater than, not less than. So because of greater than, so you can simply throw away 1 over n squared. Because if you throw away 1 over n squared, then the sum getting smaller, okay? It's getting smaller. So therefore, instead of working on this 3-term inequality, now you can reduce 2-term inequality. Once you solve this 2-term inequality, will automatically satisfy the previous inequality. Okay, now this only, so this means for the inequality side, this the case 2 is simpler than the case 1. Okay, now you can solve for n. Okay, so you get the 1 over n is less than s squared minus 2 divided by 2s. This means that if 1 over n satisfies this, then s minus 1 over n squared will be greater than 2. Okay, now such n exists, again, this is guaranteed by the corollary 1.ab. Okay, because s squared minus 2 divided by 2s, this is just a positive real number. Okay, that's it. 1 over n is less than that. Okay, so you can see that I got the existence of n, so that s minus 1 over n squared is greater than 2 is in the gap. And now I can use this in the proof. So you can say that by the corollary 1.ab, there is n such that 1 over n is less than s squared minus 2 divided by 2s. Okay, so this is guaranteed by this corollary. Now because of this, so you work backside, okay, so you can see that s squared minus 2s divided by n is greater than 2. Therefore, the s minus 1 over n squared on expansion greater than s squared minus 2s divided by n is greater than 2, okay? So using this procedure, you get an n so that the s minus 1 over n squared is greater than 2. So this is what we want. Now, the hard part is that how can we see a contradiction from there? How can we see a contradiction here? Okay, previously you have s plus 1 over n, okay? So this will contradict to the fact that s is upper bound. But this time it's different. It's s minus 1 over n squared greater than 2, okay? So you cannot use the previous argument to continue. You have to think something else, okay? Now, how do you think about this? Okay, you have to keep focusing on the assumption that s is the least upper bound. Now, if you think about this way, so since s is the least upper bound, okay, so any smaller number cannot be upper bound. So in particularly, you can see s minus 1 over n is not going to be upper bound because s minus 1 over n is smaller than s. Now, if s minus 1 over n is not upper bound, so therefore, okay, so here saying that claim that s minus 1 over n is not upper bound. So this means that there exists element in s such that So this element is denoted by t. T is greater than 1 s minus 1n, right? This is reason because s minus 1n is not an upper bound. Okay, so from this gap, the existence of n inside this gap, I can conclude that there is a t in S. T is greater than S minus 1n. Now this will give us a contradiction. Why? Because then you know that T is in S, right? T is in the set of S. And T is greater than S minus 1n. Okay, now I'm going to square on both sides of this inequality. Then I'll get this. Then you can see that the T squared will be greater than S minus 1 over n squared. Then S minus 1 over n squared is greater than 2. Okay, so that is given by the previous inequality. So this means that T squared is greater than 2. Okay, now T squared greater than 2. This thing's simply saying that T is not in this S, not in the S. Because every element in S has to satisfy the square of that number is less than or equal to 2. Now this time, T squared is greater than 2. Okay, so this means that T cannot be in S. So therefore, this contradicts to the fact that T belongs to S. So that's a contradiction in this case, the case number 2. So this the contradiction in proof actually finished the proof of part 2. So combining part 1 and part 2, so this will tell us that S squared has to be equal to. Okay, so that's a proof of the entire theorem. Okay, so this is our main goal today. I mean, I'm trying to show you the detailed proof. And I firmly believe that you need to spend time to review the entire argument to get familiar about it. Especially in the part 1 and the part 2, you have to understand really how we get this contradiction. Okay? Any questions? So I intend not to continue at this point. So I want to, so maybe we can finish early. I mean, so you can spend more time working on this theorem by reviewing it, okay? And next time, I will maybe come back to this again to indicate some important points, right? Any questions? If no questions, I think I should stop here. Or we can finish early. And I'm going to make sure the video is ready in half an hour, and you can review it by yourself. All right. Okay.
Thank you.
Okay. Thank you. Okay. All right.